So we're the precision positioner system. I'm Brett Revelle, the team lead. Matt Raposa is our computer and electrical engineer. Chandler Mitchell and we have Fabio Souza, who are both mechanical engineers. Our faculty advisor for this project is Don Foster, and our customer is Cameron Karchi, and he's part of Harvard Medical School's Department of Ophthalmology, also Mass Eye Ear, and we've also had tooling from Spectrum Lighting. So we'll get into the nitty-gritty of this project, and definitely nitty-gritty. So, so our problem statement is mice are used to simulate eye dropping in humans because mice have similar ocular structure to human beings. And the ooh, did that just go up? That's weird. It's coming back. No. Awesome. Oh, okay. Jiggle the cable. Okay, cool. The mouse is back. So, robotic surgery has been a thing for a while, and that's just because people are imprecise, and machines are very precise. So, a group last year. You want to just hold it? Yeah. Awesome. So, the group last year was tasked with building this project, and they did a really good job. They made a really firm mechanical substructure with 3 camera mounts, and they used an Arduino, and they used a lot of really nice mechanical parts, which we use in this year's design that you'll see later. But it didn't have any software to interface with it. It didn't have any external power supply. And also, it used a breadboard, and the wires fell out when demonstrating to the customer, and they were unable to demonstrate. Okay, cool. And they were unable to demonstrate. So we decided to kind of do it a little bit differently this year and use parts and firmware that are readily available and easier to access than what they were doing previously. Also, we made a concerted effort to document everything we were doing. So I'm going to pass the microphone off to Matt.
All right. So for our constraints, we have the physical gearing of the system itself. So our torque specifications on the motors had to be enough to actually move the system. The mouse also needs to be placed on the gantry system with its eyeball facing the system to actually perform it. That's up to whatever lab technician is using the mechanical system. Mechanical slip in the gears was an issue, as we'll see in our results a little bit later on. And the rotational limits of the gantry will hit our system if rotated too far. And our applicable standards are all the IEEE wire standards and all of that, as well as the mechanical ASME standards, AGMA for the gearing, and the ethical handling of the lab mice. So our customer requirements for that need to be accurate, precise, and repeatable, because if it's not doing its job. And needs to be programmable in the X, Y, and Z axis on using its own software. It needs to make quantitative measurements. We need to know what those are so that we know that it's accurate, precise, and repeatable. We need a homing mechanism so that we can always send it back to the same position and able to send it from there to the mouse. Computer-aided software, ability to capture and save images so that we can see what's happening and record that. We have 2 cameras set up currently doing that. And accountable if there's a failure. Then there are engineering requirements, which is just a little bit nitty-gritty, more into the details from our customer requirements. Most importantly, our precision within 300 microns, repeatability within 150, and accuracy within 100 microns.
And so we had last year's injection system assembly, and that kind of didn't really change. We changed a lot of mechanical features to make it work better and to make it more accurate and precise. So we were using a RAMPS 1.4 shield, which is a board that's used to control 3D printers from an Arduino at Mega. You can send the shield G-code command. So we decided on using G-code as the interface language because CNC machines are incredibly precise and so are 3D printers. So if we were able to send it coordinates from a coordinate system, it would be incredibly precise and repeatable. So we also had a vision subsystem, which are 2 cameras hooked up to USB hub, which connect to the computer. And we had a software interface as well, and we'll get into that more later. And it was also all controlled by a power supply, so we didn't have the issue that last year did with burning out their stepper drivers and causing a large issue during live demonstrations. So we had 2 mechanical subsystems, and I'll go over the electrical alternatives. So we have this processing subsystem, and that's really the question of how we're going to drive these motors. And we were debating between using the RAM shield that we ended up with, running a firmware for 3D printers called Marlin, and we were also debating using something called Gerbil Shield, which is the shield used for CNC machines, and also using a firmware called Gerbil, which is used for CNC machines. And we already tested it with the shield, so we weren't too concerned.
So for our mechanical alternatives, we had two alternatives for the gantry. The gantry is the part that rotates the mouse. For our first alternative, we had a two-piece setup. One is mounted to the system itself. The second piece would be able to slide out, so that way they could position the mouse away from our system and then just place it into position whenever they needed to. And we had a second alternative that Mitchell did.
So our second alternative was to make just one piece. In both designs, we were trying to make it as hands-off as possible when dealing with the rat or the mouse. So that way, this was kind of like a scoop idea where we basically cradled the mouse in a kind of a nurturing way. But ultimately, we felt like the two-piece design was what we would go more along with. So that way, we could again be more hands-off with the specimen.
So for our evaluation of the design for the mechanical portion of it, for the gantry, we decided to almost combine the two of them. We stuck with a two-piece design. That way they could stay away from the system while they were loading the specimen. What we did do was add the cradling portion to the slide that slides into the gantry base. That way they could still cup the specimen as best as they could, and then that would then slide into the base.
So for the electrical alternatives, we needed motion control, and both of the alternatives provided us motion control, but Marlin, as a firmware, provides a little bit more robust motion control on the extruder axis, which wasn't a thing for the Gerbil Shield. It only rotated 3 axes, and we appropriated the extruder axis to be used for the rotational platform of the mouse that's on the left. We also needed the ability to set it at a home position, and that shield had a lot more homing switches on it. And then the last one kind of worked for both of them, but we ended up using the ramps because it's more modular and we can replace the stepper drivers if they fail, which they definitely did in testing. So as far as the technical design, we designed a piece of software from the ground up using Qt as the interface, and then we were using PyQt to port that over to Python, and it creates an abstract layer on top of Python, on top of Qt, that allows you to connect all the buttons on the screenshot on the left to Python buttons that are used for PySerial to communicate with the firmware. And all it does is it sends a G-code command to tell the machine to move left 8 units, and the machine will move left 8 units. And we had a vision system that we didn't quite get to finish, and we'll talk about that more later using OpenCV to put the grid on to the mouse's eye for quantitative measurement.
So electronically, we're using the RAMPS 1.4 shield with an Atmega 2560 chip, and on that shield are 5 DRV8825 stepper drivers, and each of those needed to be tuned for our motors. So those have variable amperage output using a potentiometer. So the way to test those is testing voltage at the potentiometer. Our larger motors operated at about 1.5 amps. So those were tuned to 0.6 to 0.9 volts, and our smaller motor for our needle axis was tuned to 0.3 volts because that motor was much smaller and didn't require the same amperage output. Now, on the realm of end stops, our X and Y axes use a mechanical end stop system. So at its max and min, the system will move up and press that switch in and send the signal to the ramps board, stopping the machine. And on the needle axis, we use inductive proximity sensors. So that just senses whether or not there's a bit of metal over it. So as that metal slides back, it will go over that inductive proximity sensor and trigger it. Those sensors operate on 6 to 36 volts, which our Arduino board could not output. So we had to use an external power supply at 12 volts, and that voltage needed to be stepped down to 5 volts so that we could input that into the mega. So what we did was use a pull down resistor, 10K ohm, and that pulled our 12 volts down to 5 volts for the signal line. So we ended up inputting that to the board, and that triggered it properly. And that circuit you can see on the top there. And let's see, what am I missing here? I don't know. It was a bad time. We're gonna move on.
Oh, you good. So this is the redesigned and the major mechanical components. Here's the base again on your left side, and the key features are loading the specimen and being able to load the specimen in the exact same position every time. With this design, there's no restraints required for the specimen. This places the specimen with the eye facing the needle every single time. And the chamfer in the slide design allows for the mouse to be cupped. In the middle, we have a motor mounting bracket. Our original system did not allow for much movement into the mouse's eye. What we did was design a bracket that would allow us to mount the motor, which we repositioned, in a position that allowed better range. And this allowed the system to have a full free range and move with all the axes. It was lightweight, and I think that's it, sorry. And then the last one is the shaft. So we needed a shaft to transmit power from our motor to the track that moved in and out of the mouse's eye. So what we did there was I discussed with the machinist a lightweight material and a material that can handle the torque coming from the motor. So we designed a shaft made from 6061T6 aluminum that would allow for the gear to move in and out of the eye easily.
So here's actually a list, or not a list, but a few diagrams of the different parts that we had to make in addition for this year. As Fabio said, we actually had to move a couple, one of the motors around because it was driving into the machine, or the system itself. So we went ahead and designed a bunch of different brackets that would help clear up the space on the system, allowing for easy access to get to the specimen's eye. And then if you see on the bottom row, those are all brackets that will hold our limit switches in place to keep the system able to move in the X, Y, and Z axis. So for testing, we also did gantry testing, motor mount testing, and shaft testing. It's pretty much straightforward. We just wanted to make sure that the system had the ability to move in, again, the X, Y, and Z axis, and have the freedom for the lab technician to get in there and actually have to manipulate the rat if needed. So one of the things that we did was make sure that the driving system was actually driving the shaft and the worm motor, or in the worm to rotate the gantry itself, allowing for that easy access. From there, we actually did precision and reliability testing, and I'll turn that over to Brian.
So for accuracy and precision testing, we use an SPI IP65 distance measurement tool. It's a digital display that can measure down to 0.001 millimeters. So here's the exciting part for me, at least, our results. So as you can see here, we had to calibrate our stepper motors. So what we were trying to do, at least, was send it 1 millimeter forwards. And in firmware, that translates to the number of steps for the stepper motor. So each of our motors, one step is 1.8 degrees, but for us, inheriting the gearing from the previous group, we had no idea how far 1.8 degrees would actually move the system. So there's a little bit of trial and error figuring that out. In the first chart here, that's actually at 200 steps per unit. A unit for us would be 1 millimeter. And we'll see in a minute that it did not move 1 millimeter. On the x-axis, it was around 1.14. Y was a little under a millimeter on average. And on our z-axis, or needle axis, it was around 0.5 millimeter. So by editing steps per unit forwards now, the measurement that I did was taking 1 over our average to get a ratio, and multiplying that by our original steps per unit, I could get a new one to work off of. So then, for instance, we started at 200, then I went to 163 on the x-axis, worked our way down, much closer to 1 millimeter this time, and then again. So this last chart here should be the most accurate. So for repeatability, if you can remember back to our requirements, repeatability needs to be within 300 microns, and our standard deviation down here, we have 30 microns on the z-axis, 20 microns on the y-axis, and 40 microns on the x-axis, which is well within what we were looking for. And on, see, in precision, we wanted within 100 microns. So clearly we can see that as well in standard deviation. And for repeatability, repeatability was 300. I'm sorry, I forget what I said originally. But the max to min difference there was around 200. It was there. So we were actually hitting all of our repeatability, accuracy, and precision requirements from the customer. And actually, well, I'm going to go back here. Well, I was. In the graphs, we can see each of our trials getting a little bit closer to that 1 millimeter mark on each axis. And what's interesting to see was the dips here. So what I figured that out to be was mechanically there were some slips in the gearing. So there may have been a flaw in the teeth. We're not exactly sure. We inherited that from last year. But that would be definitely something to look at going forward with the project and future work. And you can see the same thing on the y-axis. There's a big dip there as well as in there. And on the z-axis, clearly I didn't start it in the same time with each trial. There's a dip there that matches that one and that one.
Cable.
Yeah.
Cool. So we also did other test results that really corresponded with the software. So the motors and mechanical system are the test that Matt was talking about. The eye orientation test is, can the gantry move in such a way that the needle can come towards the mouse's eye. We did camera testing for do they initialize and can they both be displayed at the same time, which actually turned out to be a larger issue than we thought. We also did testing with the limit switches. Can every single limit switch be triggered if the machine moves past its rotational limit? And we also did an emergency stop, which retracts the eyedropper axis first, so it pulls the needle outwards, and then it moves the X and Y axis away from the mouse as fast as possible, and cuts off the power as well. So our overall schedule is quite delayed. We had issues with mainly integrating all of the systems together at the end. So all the systems were being worked on simultaneously, and then we decided to put them together at the end, which wasn't the best idea because when we came down to testing, there were things that didn't work. So for example, the syringe axis moved right over the proximity sensor, which came in contact with the gantry, and they were all meshing together, and that was something we didn't foresee when we were building it initially. So some lessons learned is we have to deconstruct the previous team's work, and we did. And we kind of reverse engineered a lot of their design choices, and we were fortunate to have their notebooks, and we really read through the notebooks and tried to figure out what they were doing and why they did what they did. We also figured out that it's better to overestimate time than underestimate. We severely underestimated our time for this project, and a lot of the integration and final testing took a lot of time. Also, documentation for everything takes a lot of time, and that also put us over on time. So in summary, we really think that we have a much better system than was produced last year. The system is now repeatable, which is nice. It's controllable with software for a laboratory technician to use. There is a vision system integrated into the software, and the system knows where it is in three-dimensional space due to limit switches. For future improvements, we'd like to add a quantitative measurement system into the vision system. We don't have that currently, but that's something that should be added. Also, the gantry axis does not have end stops, and that's something that we would like to add as well. So we have a short video, hopefully the cable will hold in there, of the system, and it's not completely lined up, the video on timing, but you can see from the video screen on the right that's the software, and you can see it moving it away from the mouse, and then different directions as well. So it moves away as far as possible until it hits the limit switch on the back, and then we have it just moving up and away. It's a bit more visible on the bottom screen. So, cool, questions?